Yeah, so great to see still many fresh people. Second day of the of the conference. So we are moving to the session on environmental characterization and climate change. There are 5 fabulous speakers, guys. Give them the hands before I tell you who it is. Yes. And I am a secret admirer of all of them. And the first one comes Boris Parent, ecophysiologist from INRAE. Cannot wait for your presentation.
So good afternoon, everyone. Thanks, Fred, for the invitation. So I'm really happy to be here, especially because I've seen a lot of potential outputs from the talk before for the work I will present right now. So this talk is about the environmental characterization of maize European trial networks. So it's part of the European project Invite, in which we were implicated with some of you also. So I think we're all here to try to to analyze, predict, etc., the G/E interaction at large scale. And for that, we have a lot of tools. Of course, we have tools for describing the genotype. So the genotyping can be cheap at high scale, etc. And more and more are developing some phenotyping tools to do that. So at a large scale also. So in the field, in control environment, in platform, etc. And so the Envirotyping, to be able to answer the first equation, the Envirotyping could mean that we want to characterize the plant microenvironment at high throughput, like for the other part of the equation, and with the idea of summarizing this information in the simplest and most informative way. So that means as coming from a temporal series of quantitative environmental variables, which could come from climates and management, and come from sensor, database, remote sensor, etc. And from that, the first step is to find a set of indices which summarize this temporal series in relation to the plant developmental stage. And to go further is to describe, to determine environmental scenario, clusters of environment with similar environmental indices in which we expect to have no G/E interaction. So we did that for in the project Invite. So in the VCU trials in Europe for the last 15 years. So the data set has been presented by Jeep yesterday already. So you have seen that we have different network, one per country, and different maturity group. I will present is on maize. So you have here the map of the different trials in different countries, so the network of VCU trials. And for the first question was to deliver environmental indices for later G/E analysis, for mixed model analysis, etc. And also we had another additional question. Can we capitalize on this different network at the European level in order to maximize the chance of evaluating varieties in dedicated scenarios? So the first problem was that at this European level, we had a large range of maturity groups. So from, of course, early variety in the north, late variety in the south. And of course, the crop environment depends on this earliness, because of course the flowering, for example, will not happen at the same time for different maturity group in one site. And the second problem was that the definition of the group of maturity were different, were depending on the country. You can see here the different groups in different country, how they relate to the FAO indices. So we had first to organize a new maturity group which could be valid over across Europe. So it's what we've done. So you have this example here. You see so that has been done with real data, of maturity or flowering time. And you see where the different groups are per country, and the dashed line separates the different new maturity group, what you use for this analysis. And here the map or where this maturity group are grown with, of course, the earliest variety in north of Europe and latest variety in south of Europe here. So which environmental indices? The first thing that we've done in order to decrease a bit the dimensionality of this temporal series is to separate the crop cycle into 4 periods. So crop establishment, the vegetative period, the flowering period, and the grain filling. And in each of this period, we calculated a list of environmental indices. There are in reality more than that, but they are all related to either radiation or soil water status or temperatures. And so to reduce the dimension of this data set, the first idea, of course, I think we will all have this idea, is to use a PCA. And of course, you see that we have many correlations, especially all the variables linked to, for example, water deficit are linked, and the same for temperature, etc. You see that the first dimension explains 41%, if I read well. So the problem is that if we go to a farmer or a cooperative, etc., and we say that this genotype is really adapted to PC1, it's not really useful for them. So we need more intuitive indices. And the same, I think the first idea, if we want to cluster scenario, to have environmental scenario, is to do K-means clustering based on this data. And here again, so the first problem was that it's really highly dependent on the data set. Each time we use a new data set, the clusters were completely different. Again, we have non-intuitive scenario because that mixed some variable linked to radiation, to that of temperature, to water stress, etc. So it's not quite clear. And again, we can lose some rare scenario. For example, we don't have any cluster with high temperature, but high and also high PTQ, for example. So, and that could exist in the European environments. So we lose this rare scenario, which are perhaps interesting. So what we've done is to select 3 indices representing 3 types of environmental variables. So one for radiation, one for soil water status, one for temperature. It was based on the effect on yield with BLS. And here are the results. So you have different indices here, and the value for here is the crop establishment, vegetative, flowering, and grain filling. And the bar are when it's average on a larger period. And so we selected the indices which is low radiation during the whole crop cycle, the soil water status at flowering, and the high temperature at flowering and grain filling stage. And from these indices, in order to group, to make scenarios, we use the full factorial of these different indices. So here you have the distribution. So it's here this time is all over Europe. You will see per maturity group later. So here you see the lower radiation. So you see that the gray one, the scenario with the low radiation are here and the high radiation are here. So we separate each time in 3 different levels. We've done that for radiation, temperature, and water balance. And you see the different probability to obtain this scenario in different sites in Europe. And the factorial of this 3 groups by 3 variables means 27 scenario. And we have these probabilities different depending on each site and depending on crop management. Of course, if we are in well water condition, the water balance will change. And different probability also regarding the maturity groups. So it's what I show you here. So for example, for the group, for the early genotypes, you have low radiation. They are in north of Europe here, mostly low radiation, but we'll also have a probability of having high radiation and low temperature, but we can have also sometimes high temperature, etc. And if I go like that with going to later and later variety, you see that the proportion of the different cluster of indices change. And of course, if I go to the late variety, we have, of course, less, it's in the south of Europe, we have less environment with lower radiation. And so we have the ratio of the different scenario in the different networks. And here an example for Belgium. So we have here the majority scenario. There's some empty space, so that means that this scenario, we cannot get them in Belgium, and we have rare scenarios. So from the probability of having this different scenario, we've done what we call Envirotype or agroclimatic zones, which are defined by the probability of having each of these level of radiation, temperature, and water balance. So here for the different maturity group, in rain-fed or irrigated condition. So of course, if I take here the Envirotype 1, we can say that's high probability of having low radiation, low temperature, and moderate water balance. These environments are in north of Europe, to the opposite to the second one with high radiation and high water deficit. This Envirotype 2, we can find that more in south of Europe. So can we use now this frequency of occurrence at each site to optimize a trial network? So the idea is to be able to capture in a secure way this rare scenario. So if you have here the efficiency of a network to capture the different scenario, and here the number of trial, of course, if you increase the number of trial, will increase the probability of having all the scenario. But the idea here is if you have a given position, so a given number of trial, how can we increase that percentage of chance of having more scenario or a given scenario? So I give you just an example. So it's for this group M3 in France. That means the early, late variety, maize variety in France. For rain-fed environment, so I use two criteria. One is the homology. So it's if the network represents well the frequency of the scenario in one zone, for this zone here, M3 France. And the presence is the percentage of possible scenario in one zone. And what I show you here is something like theoretical. So it's a bootstrap of all scenarios that we observed in the original dataset. So you see, of course, if we increase the number of trials, either with site or years that increase, either the homology or and the presence. But now, if I take real years, so 1 year or 2 successive years or 3 successive years, you see that we have that pattern. And what is important to see is that we always lower than what I call the theoretical line, the theoretical mean, the blue one. So we are always under this line. That's why it's because the climate is really structured by years. So there's environmental tendency, change, and the probability of having two similar years is higher if the years are successive. And another way of showing that is that if we for the same number of trial, to have 1 year, so for example, 10 sites during 1 year, or 5 sites during 2 years, etc., you see that each time we increase the percentage of presence if we increase the number of years. Again, it's because this environment is restructured by year. So it's always better to have more years compared to more sites. And here is an example with real networks in France, where you see that some years everything is really happened really good, like in 2006. With only 10 trials, this year capture half of the possible scenario for this group M3 in France, but in some years it's really bad. So the idea is how we improve that. And so I give 3 examples of optimization. The first one is what happens if we use irrigated site, even if we want to capture a scenario for rain-fed environment. Here you see that if we use irrigated site, the homology decrease, of course, because what we want to represent are the rain-fed environment. But you see that the presence is perhaps even better if we had 1 or 2 sites with irrigated condition. Another possibility is to use other sites in France, so a bit further north or south, and again with well water condition or under rain-fed condition. So for the homology, it's always better to have more here M3 rain-fed, so what we target, so that's normal. But if you look at the presence of the different scenario, that's also good to have sites more in the north of France. We capture more scenario if we have these sites here. But we can see that here. So here is a Pareto front between this percentage of presence and homology. So the one you have to look at is the orange one, this Pareto front. And of course, if we want to optimize the homology, the best will be to stay within the rain-fed M3 group. But if you want to maximize the presence of different scenario, it's good to have sites in the north and in the south in rain-fed and well water condition. And of course, you have the intermediate value, so it's probably there that we have to find the best trial network. And so the last optimization is just an example again, but if we want to cross border and to include sites which are, so here it's in Germany and in Hungary. And so now the Pareto front is the blue one, so we improve both the homology and the presence by having some sites in Germany and Hungary. You have some results that are, I think, quite interesting. Again, if we want to have best homologies, it's good to be in France, in rain-fed, but having one site in Hungary is also really interesting. And again, if we want to maximize the chance of having a lot of different environments, to be in north of France, south of France, and Germany could be a solution, and probably that the best solution will be intermediate here. And so here are these 3 types of optimization. So here are the real sites that I presented to you before. Here are the theoretical one. You see that it's more or less the same. And the 3 optimization. What you can see is that we don't improve a lot the presence, so we are not able to capture really more scenario. But what you can see here is that the terrible years are not here. So the chance to have the risk is lower. The chance of having 1 year with all sites having the same scenario is, of course, a lot decreased here. We don't have this terrible year here. And so what next in this project? First, we do the same in wheat, same kind of analysis in wheat, and we use a crop model for that with model-derived indices using serious quality and serious maize. And we try also the generalization of this approach in order to optimize network trial networks. And we want to do that for both the current environment and future environment. In other words, means that can we define a trial network for current conditions that can mimic the future condition for a specific target population of environment. And that's all. Thanks to for listening. And so all these data are coming from European Office of Variety Registration. So thanks to all of them. And this work is mainly based on the work of Theophile, who was an engineer with us at LEPSE in Montpellier. Thanks.
That was absolutely brilliant, Boris. Thank you.
Thank you.
So we have a time for maybe 1 or 2 questions. Who wants to start? Otherwise, I will ask, and that may not be so nice.
Yes, thank you. Thank you for the presentation. It was really nice. I had a question about this optimization and using trial sites in other countries. Did you also look into using M3 sites in other countries, since you tried to select sites for the M3?
No, that was just an example. Now we try to optimize, so to generalize it and to have all possible optimization with specific location. That for the moment it's a bootstrap of trials in another country. I didn't select one specific site, but perhaps some precise site could be really useful. So it's what we will do. Yeah.
Yeah, thank you.
Mm-hmm.